teachers this question, asking them about a challenge that they overcame and what it was that helped them overcome the challenge, there's often a combination of knowledge that they've brought to the challenge, skills, and attitude. And if we had a lot more time, I'm sure that if we had that conversation here, you would also remember drawing on knowledge, skills, and attitude. And I'm mentioning this because at Enrich, we find this model of what makes successful mathematicians really helpful. So I just want to talk to you about the rope model that we refer to. I noticed some of you are taking photos. There's a page on the Enrich website that I'm going to show you very shortly where you'll find all the slides and all the resources. And it's freely available, you don't need a password, so everything is going to be on one page with links to it. So don't worry about having to keep a record as we go along. So the reason I find this rope model really helpful is that it draws attention to the knowledge, skills, and attitudes that mathematicians bring to problems. But it also suggests that for a rope to be strong, these 5 threads need to be working together, need to be working in collaboration, and that they're all equally important. And that seems significant. All the threads are of the same thickness, and they combine to make a strong rope. Now, I suspect that when many of us were at school, our teachers and textbooks focused on just 2 of the threads. So the middle thread, which is about understanding concepts. So when you're working on angles, you know that you're working on the amount of turn. If you're working on decimals, you know you're working on representations of numbers in between whole numbers. Or if you're working on area, you're thinking about the amount of space that is covered by shapes. And having understood or being introduced to a concept, I imagine you then spent most of your time on the thread on the far right, which talks about a fluency with standard procedures, with standard algorithms, being able to solve standard problems in standard ways. And for many of us, that was the full diet of mathematics that we had when we were at school. What the rope model suggests is that there are another 3 threads which are equally important. On the far right, adaptive reasoning. We need students to be able to understand, explain, articulate, communicate, justify, convince, sometimes prove. These are all particularly valuable skills in mathematics. But as Usman was saying, we were at lunch the other day talking to Dr. Ali Chima, the Vice Chancellor, and he was saying, actually, this is important for all our students. We need them to be able to communicate their ideas. We need them to be able to explain their thinking. So it's a skill which is not just about mathematics. The second thread is to do with with strategic competence, which is about solving problems, knowing what to do when you come across a problem that you've never seen before. So I suspect most of us were drilled into and prepared for solving standard problems, but what happens when you get given a problem you've never seen before? And I think this is what horrifies Uzma, that I might give her a problem that she's never seen before and put her on the spot. And actually that's terrible, that an intelligent, thoughtful, articulate adult who does a demanding job feels this anxiety about a subject that ought to make sense to her and to all of us in this room. So, preparing students to be problem solvers is again something that Dr. Chima mentioned, how important it was for the students who arrive at LUMS to be prepared for that. So, those are 4 of the threads. The final thread I want to talk about is the one that talks about productive disposition. And I suspect many of us became teachers because we wanted our students to leave our classrooms and to leave our schools feeling positive about learning, positive about the subjects that they'd studied, positive about themselves as learners who are going to carry on learning and value learning. So when I showed you that first slide about overcoming challenges, attitude is really important. And we want our students to leave our classrooms and our schools with a positive attitude, not worried about mathematics, not worried about themselves as learners of mathematics. And so I want to focus today on what teachers can do in their schools so that when their students leave, they leave as examples of strong ropes who can work collaboratively, who can work on problems, who can draw on their conceptual understanding and the procedures that they've learned, and they can work in a positive, enthusiastic, optimistic way, rather than in an anxious, worried, defeatist way. So, I'm going to go to a page on Enrich. All the pages on Enrich have the same URL until the very end. Every page on Enrich starts enrich.maths.org, and usually after the / there's a number. So let me take you there and show you. So if I go to enrich.maths.org and I type in the number of a resource that I know, I happen to know the numbers of 2 problems. One is ID 900, and it takes you to a problem called attractive tablecloths. There we are. Took a while. Now notice, I haven't had to use a password, or I just came up here, plugged my laptop, went to Enrich. Your teachers, your students can do exactly the same. And actually your parents can too. All the resources on Enrich are freely available, and you don't need any passwords or permission. So we've got resources for teachers, early years, primary. Usman was talking about the importance of starting young with students, but also for secondary and post-16 teachers and for their students. And we've also got some resources for parents. Usman was talking about having young children. With Amanda in the car yesterday from Lahore, we were talking about how as a parent, when her son was younger, actually they did a lot of maths at home. And there are ideas on these pages. So if you want to encourage your parents to get involved with their children, do point them in the direction of these pages. Okay, so I've set up a page for you and for the teachers in Lahore and Karachi, which is, it's not very clear there. Let me just change the URL. It's enrich.maths.org, Pakistan, 2024. I'll put 2024 just in case you're invited me again, and then we can have a different. It takes about 10 years to invite me, so it'll be 2034 next time. Okay. So, there's a link to the slides. So everything on the slides is available. There's an image of the rope model. And if you want to know more about the rope model, or your teachers want to know more about the rope model, there's a link there to a short article that a colleague and I have written. So I'm going to talk about 5 principles, or guiding principles that inform the work that we do. And you may be asking yourself, why has Uzma decided that we're going to focus on maths on a day like today, rather than on whole school issues? And it seems to me that maths is often one of the subjects that is not very well taught. There was a colleague who worked in Cambridge for a while, did a PhD in Cambridge, and when she went into schools and talked to students, they described maths as being tired. T-I-R-E-D. T, because they found it tedious. I, because they were isolated in their classroom. R, because it was all about rote learning. E, because it was elitist. And D, because it was depersonalized. So tedious, because it was just repetitive. You were shown how to do something, and then you did lots and lots and lots of very similar examples. And I'll talk about that later. Isolated, because everybody was working on their own, with their heads down, and there wasn't much opportunity to discuss work with other students in their class. Elitist, because the schools often gave the impression that either you were good at maths or you weren't good at maths, and it was great if you were good at math, but there was nothing you could do if you weren't very good. And that was a really destructive message to be giving to so many students. And depersonalized it wasn't a creative subject. There wasn't an opportunity to express oneself. And that this was very, very different to how other subjects in schools are taught. If you imagine going to an English class and reading a poem or a Shakespeare play, there are opportunities to discuss with other students your interpretation of what's going on. There are opportunities to share your ideas. No 2 lessons are similar because you're working on different ideas and different texts. There's a lot more, there are many more opportunities of involving yourself, engaging than there are in maths. Somebody I was reading the other day, and of course the same could be said about sports, about music, about science. In those lessons, children are working like musicians, like sportsmen and women, like scientists, carrying out experiments, coming up with hypotheses, testing hypotheses. So a scientist coming into school will recognize that what children are doing is very similar to what the adult scientist does. But that does not happen in maths, because the mathematicians are working on all 5 threads of the rope. But in schools, often the focus is on just 2 of the threads. So in order to work on all 5 threads, build expertise in 5 threads, I want to talk you through the guiding principles. I was reading something the other day, and they said, actually the experience of students in schools is often that they're studying fossilized mathematics. Whereas in other subjects, it's live. Whereas in maths, it's all set already in textbooks, and all they need to do is look at what's been done before. So I want to challenge that model. I want to say, actually, maths in schools needn't be this fossilized subject that it is for many. So here are the 5 guiding principles. Valuing a growth mindset, making sure that everybody feels that maths is for them, maths is for all, allowing time for exploration and discussion so that students can be creative, giving the message that there isn't just one way of doing things, of solving problems, so encouraging multiple representations and multiple strategies, and importantly, if students are going to work like mathematicians, offering students the opportunity of going on mathematical journeys. So I want to spend just a little bit of time on each of these, and the colleagues who've seen me already, I start getting a bit excited about all this, so I'm going to take my jacket. Okay, so Carol Dweck wrote a book called Mindset, and I put a link to Mindset at the bottom of this page, along with a few other references that you might find useful. Joe Bowler's written about mathematical mindset. Some of you might have come across Malcolm Gladwell's book, Outliers, and then there's Francis Sue's book that I imagine we'll talk about when we get to the panel, if Usma asks me the same question that she asked me yesterday. Okay, so what's important about Carol Dweck's work? She found that children who get taught by teachers who have a growth mindset do better than students who get taught by teachers who have a fixed mindset. Fixed mindset means your intelligence is fixed. Growth mindset means you can make progress, you can learn, you can improve. Joe Bowler talks about a teacher who had a poster in his classroom wall, and it just had one word, and the word was yet. So whenever students used to say, I can't do this, the teacher insisted that they rephrase and say, I can't do this yet. And it changed the culture of the classroom completely. So the messages that we need to give to our students is, it's okay to make mistakes. Learning is a messy business. I mean, that's why we're at school. If we could do everything without making mistakes, then we don't need to go to school. We go to school to make mistakes and then learn from them. As teachers, we can offer help, we can offer scaffolding, but I don't want to do the thinking for them, especially if the thinking is within their reach. So, I want to work through a few maths problems and give you an example of how one might start with students. So the first problem is called Got It, and I've got it ready here. So in this game, we're allowed to use the numbers 1 to 4, and I'm going to play the game against the computer, and we're going to take it in turns to choose a number from 1 to 4, and the computer will just keep adding them, and we'll have, you can see there's a total. And the challenge is, can we get to 23 before the computer gets to 23? So that's the challenge. So I'm going to make a start. The computer's been very generous and allowed me to start, and I'm going to kick off with 4. And the computer's turn, and the computer's added 4 and has got to 8. So I'm going to choose 2 next. The total is 10. And the computer's chosen 3, got to 13. I'll choose 3 this time and see what happens. Computer's chosen 2, got to 18. I'll choose 2. And the computer's got to 23 and 1. Now, I do know how to beat the computer, but I want to start the lesson with students, giving the impression perhaps that I don't know. They obviously don't know. And now I would give students an opportunity of playing the game, because I think that if I give students the opportunity to play the game sufficient time, they will work out the strategy for themselves. And I want students to have that message, that they can make progress without me having to demonstrate. So when I was a student, the teacher always walked into the class and explained everything to me before letting me loose on any problem. I learned to become very dependent on the teacher. I want the students to become independent of me to be able to think. I want them to have the experience of working on a problem like this and discovering how to beat the computer. We will come back to this. Here's another example. Imagine that there is a treasure hidden on this coordinate grid, and we've got to find it. So I'm going to type in the x coordinate and the y coordinate. Tells me how far across and how far up I go along this grid, and see whether I can find the treasure. I'm going to go somewhere in the middle. I'm going to choose 5 across and 5 up and see what happens. Okay. I'm told I'm 5 steps away. 5 steps away means I could go from there, 5 across, and the treasure might be there. But I could also go 5 up from there, or 5 across in that direction, or 5 down. But I could also go 4 across and 1 up. Okay, or I could go 3 across and 2 up, or 2 across and 3 up, or 1 across. So from this point, I could go 1 across and 4 up, or I could go 2 across and 3 up, or 3 across. And you can see that there are lots and lots of possible. I'm going to do this quickly, just to show you all the possible places where the treasure could be hidden. And all these are 5 steps away, because whenever I'm walking away from that 5, I'm never walking and coming back to it. Okay, so I've reduced the number of choices. I'm going to choose a point. What shall I choose? I'll choose 7-2 here. So I'm going to type in 7-2. I hope the treasure's not here, because that will spoil what I want to say. Okay, good. I'm 4 steps away. So, okay, so it could be that I go 2 across and 2 up. It could be there. So it can't be there. It can't be there. That's more than 4. Let's have a look. That over there is also too far away. These are all too far away, so it's only got to be 4 away, so it can't be that one. It could be 2 across and 2 down. It could be 3 across and 1 down. It could be 4 across. I think the only places the treasure can now be, and it can't be there. Just ignore that. Okay, so I'm going to try this one here, 4-1, and see what happens. Okay, 2 steps away. That's great. So it can't be this point, and we know it can't be there. So it's got to be either 1 up and 1 across, or 1 across and 1 down. I'm going to try this one down at the bottom. 5-0. See what happens. Test the coordinates. I've got it. Now, everybody can do this. And it doesn't matter how many times you have a go. Everybody can do this. But notice that there's now a challenge saying, okay, you've done well, you found the treasure, but can you find the treasure in fewer than 4 guesses? I was quite pleased I did it in 4 guesses, but the computer's suggesting I can do better than that. Now, if I'm doing this for the very first time, I won't have a strategy for doing this in fewer than 4 guesses. But I might be intrigued, I might be curious, and this is one of the mathematical attitudes we need. I want students to be thinking, okay, give me a chance, I'm going to have another go, I'm going to have another go. And again, as a teacher, I could just tell them what my strategy is. I do know how to do it in 3 goes, but I want the students to have the experience of testing out theories, trying them out, eventually learning from that experience and working out that there is a strategy and they can solve it. Okay? So a growth mindset involves giving some responsibility to the students. I sometimes think about this as parents crossing the road with children. And when our children are very young and we get to the road, we hold their hand and we cross the road together. But as they grow older, we give them more and more responsibility. Perhaps we cross the road together, but we don't hold their hands and we tell them when it's ready. And then when they get a bit older, we say, okay, you tell me when you think we're ready to cross the road. But then when they get older, we give them some rupees and say, okay, can you go and get the bread and milk? And off they go. We want them to become independent of us. So if their only experience of doing maths at school is that they always depend on us showing them how to do things, they're not going to grow to be independent problem solvers. Okay, one final example. Kiting a square is a hard problem. It asks what fraction of the total area is shaded. And I can imagine many students struggling with this problem. And so I had to think quite hard about it when I first came across it. So what we do with a problem like this is we say, well, there are 3 different approaches you could take. And one of the approaches involves using coordinates. And so what I've done is I've worked out a solution to this, and I've set it out nice and neatly in about a dozen steps. And so what I've got for students is the dozen steps, fewer than a dozen, but I've mixed them all up. So students can then cut these strips and reorganize them into clear, coherent, logical steps that lead to a conclusion. And it seems to me that this is yet again me saying, I think you can work this out if I give you a little bit of scaffolding. Just as with parents, we hold their hands to start with, but eventually we hope they'll do it without having to hold our hand. After doing this, I might then say, put the bits of paper aside, can you now come across the explanation without the bits of paper? The bits of paper are there to start with as scaffolding, but I'm still wanting the students to do some of the thinking. Okay, let's go back to the Pakistan page. Oops, apologies, I'm going to have to drink a bit of water as I go along. I'm used to sitting in front of a laptop most of the time, rather than talking for an hour. Okay, so the next message is to do with maths being for all. I'm hoping that you can imagine students being introduced to problems like Got It and Treasure Hunt and thinking, oh, I want to have a go at this. So tapping onto students' natural curiosity is important. And we know that young children are forever asking questions. Actually, they drive parents around the bend because they don't stop asking us questions. And somehow, in schools, which should be the perfect place for them to be asking questions, because they've got knowledgeable, enthusiastic teachers who can help them answer those questions. Instead, it's the teachers who are asking the questions. We've got that all wrong. Wouldn't it be wonderful if students appreciated the value of asking questions and felt it was all right to ask questions? That is, and for mathematicians, of course, answering questions is solving problems is good, but asking the right questions is equally important. So this is a chance for you to do some maths. So hopefully in front of you, you've got paper and pen. You're going to need that. I know that many of you don't have a background in maths, so please don't worry. I know that Rusma's a bit worried, but she knows what I'm going to do, so she's looking a lot more relaxed than she did in Karachi. So I'm not going to do any difficult maths today, so, relax. So what I want you to do is this. Okay, the instructions are on the left. I want you to choose a 2-digit number. So write it down on your bit of paper. So anything from 10 to 99, 2 digits. It could be 24, it could be 76, it could be 19, it could be 28, it could be 55, a 2-digit number, less than 100, more than that. Okay, next instruction. Take your 2 digits and add them together. So if I had chosen 42, I would add the 4 and the 2. I'd get 6. And the last thing I need to do is subtract that 6 from the original number. So I'm going to subtract 6 from 42. And if you've chosen 75, your digits added up to 12, you take 12 away from 75, whatever. Okay. Once you've got your answer, I want you to look at the chart on the right. And you should find your answer there. And for this to work, I need you all to look at the chart, find your answer, and stare at the little icon, which is just to the right of your answer. And what I'm going to do in a second is I'm going to jumble all the icons together. So I need you to remember what your icon looked like. Okay? So I trust you'll be able to remember. I'm going to jumble them all up. Now the computer thinks it's going to be able to predict what you were looking at. How many of you were looking at a smiley face? Hey, wait, what? Everybody? How did that happen? I'm hoping that bubbling up for you is, what did that happen there? I want students to have that experience that, oh, wait a minute, do that again. I want to talk about, did we all choose the same number? You know, Charlie talked about 42, did we all choose 42? He told us to choose a number about. Okay, children are curious. Let's tap into that curiosity. I'm going to go back to the Pakistan page. We will come back to the number jumbler, don't worry. What else have I got here? Oh, okay. So, when I say maths is for all, I'm talking about all students having the experience of finding maths accessible. And all the problems I've shown you so far are problems that demonstrate, or example, of problems that are easy to step into. So at Enrich we talk about low threshold. They're easy and accessible. You don't have to go up a big step to get into the problem. Low threshold. High ceiling, because you can make it more challenging. So if some people solve the initial question very, very quickly, you can make the problem more challenging. So for example, if we go back to got it, of course you need to play this several times before working out a strategy, but some of you may work out a strategy quite quickly, and you might decide, oh yeah, I can do this. How can we make it more challenging? Well, one way to make it more challenging is to change the target number. So instead of making the target 23, can they work out a strategy when the target is 75? Can they find a strategy when we can use all the numbers 1 to 7? So all of a sudden, we have all the students working on the same problem, but at different levels. Did the computer beat me because I went first? Is it better to let the computer go first? Is it always better to let the computer go first? Or am I better, if I know what I'm doing, is it better for me to go first? There are questions which are not very easy to answer straight away. So there is a high threshold. There's a high ceiling, even though there's a low threshold. Everybody can make a start. So the message that we're giving here is that all students have the right to shine, but all have the right to struggle. Everybody should feel that maths offers them an opportunity to struggle. To struggle, but also to succeed. I remember somebody talking about learning is about climbing mountains, not skipping over molehills. I haven't said this for over 10 years. I hope I've got this right. There is so much more pleasure in climbing a high mountain than just being given little molehills to skip around. There's no sense of achievement that comes unless you had to struggle a little bit. So let's imagine we've worked out how to find the treasure in fewer than 4 guesses. How are we going to make this a harder problem? Well, go to level 4 and hide the treasure in a 3-dimensional space. Imagine that you could go across and you can go along, but you can also go up. Somewhere in a space like this, there is a treasure. How do we find it? And can you always find it in 4 goes or fewer? That's a hard challenge. So the second message is that we want students to feel that the subject is for them. I meant to say this earlier, and I'm sorry to be doing it in the middle of this, but part of the reason for sharing these guiding principles is that I'm hoping that you'll go back to your schools and talk to your maths department, and talk to your maths teachers, and see whether these are the guiding principles, how these guiding principles compare with the principles that guide their work. And it needn't just be about maths. Surely you want the teachers in all subjects to believe that their students could do better. You want the students in all subjects to feel not just that maths is for all, but that sport is for all, that music is for all, that poetry, literature, science, geography, history, that everybody can be interested. So I wasn't quite sure why we were focusing on maths, but actually I'm hoping that the way that I've been thinking about maths can be replicated by many, many subjects, and that these conversations that you might go back and have with the mathematicians at your school can also be replicated with the teachers of other subjects. And what would be interesting is for the different departments, different subjects to then compare how this fits in with the school ethos, with your school aims. Okay, so the third guiding principle is based on an article by Alan Wigley. And there's a link to Alan Wigley's article. It's only 4 or 5 pages long. It's not a long tome. So something that your teachers might be interested in. And he compares the way that he was taught, which is a sort of path smoothing model, which is this idea that the teacher always demonstrates everything and you just imitate. And he talks about the unintended consequences of this. And we can see they're the same unintended consequences that the teachers that Ellen and Ardi found, which is that they find maths tired, they find it repetitive, they find that there's no chance to be creative. But more importantly for Alan Wigley is that the students then find it really difficult to know what to do when they come across a problem that they've never seen before. So they might be able to solve some questions, but they can't work on problems that they've never seen before. And goodness, do we need to prepare our students for problems that they haven't seen before? Think about the work that you do now, and whether your teachers ever imagined that you were going to have to face the challenges that you do. And it is difficult to anticipate the challenges that our students are going to have to face. There are environmental issues, there are wars and false news and overpopulation in areas, and there's famine. The problems that our children are going to have to face are unimaginable. I mean, there's lots of people talking about AI. I feel very unprepared to comment on AI. It's a world that I don't know and I have to be prepared for. So, Alan Wigley talks about, rather than a path smoothing model, teaching using an alternative, which is called the challenging model. And the basis of that challenging model is that you start a lesson by giving students a problem or a context, just like I did with Got It and Treasure Hunt and Number Jumbler. Giving students some time to get their hands dirty, roll up their sleeve, play with this problem, before drawing them together and drawing ideas building on the ideas, contributing how mathematicians interpret what they're saying, so that later on we can lead on to strategies, generalizations, standard algorithms and the like. So when it comes to exploration and discussion, we need to offer students some time, and what a lot of teachers do, especially in primary schools, they use this idea of think, pair, share, and they also talk, John Mason talks about convince yourself, convince a friend, and convince others. So let's go back to got it, and one of the things that might happen is you give students a chance to work on this problem. Let me refresh this so we go back to a target of 23. And you can imagine giving students a chance to play this game, and let me just revisit what we did earlier. I think I chose 4 to start with, and then I think I might have chosen 3, and then I might have chosen 2. And if students get the chance of playing this game a few times, they will find the computer always lands on 18. And when the computer lands on 18, they know they've lost. They're not going to be able to win from 18. Because to get from 18 to 23, you need to add 5. And 4 is the maximum that you can add. So if you add 1, the computer will add 4. If you add 2, the computer will add 3. If you add 3, the computer will add 2. I wish I played the piano, my fingers would be more flexible. If you add 4, the computer will add 1. So you're stuck. But that insight might only come after you've played 2 or 3 times, and you've played with a neighbor, and you've talked about it, and you've realized, I need to get to 18 and then I can win. And you're on the route, on the journey to finding a strategy. So likewise, you could play treasure hunt a few times and start seeing that you always get this square arrangement if you choose a point somewhere in the middle and you're never quite sure which way to go. And the chances of getting this treasure in just 3 goes feels really, really difficult. Can they really be serious that we can do this in 3? But at least there's the beginning of the realization that this problem needs some careful thought. Let's do number juggler one more time. Let's get you working. Let me just refresh this. Let's have a look. Sorry, I'm going to refresh it again, just to make it easy for you. Okay, I'm happy. All right, so tell you what, let's do this again and see what happens. Imagine you were a student in my class and you say, oh, can we have another go? Can we have another go? Okay, so let's have another go. Maybe choose a different 2-digit number this time. Yeah? Choose a different 2-digit number, add the digits, subtract that. Take that away from the original number, and when you've got your answer, look at the chart, look at the icon, try and remember the icon, and I'm going to jumble them all up. I hope you're ready. I hope I've given you enough time. I wonder whether it's somewhere traveling. Whoop, a bicycle. How many of you were thinking a bicycle? Oh, again. At your tables, talk to each other. What answers did you get when you did your subtractions? Can you all just compare? I got 36 the first time because I had 42 to start with. I took 6 away, I got 36. What solutions did you all get? And see whether you notice anything about your numbers. I'm going to go round and get some of you to tell me what your answer was when you did the subtraction.
For the first one, I got 36, and for the second one, I got 54.
Okay, so here we've got 36 and 54. Anybody here got something different?
First time it was 72, and the next time it was 63.
There's a 72 and a 63. And some people are recognizing that they got the same number. Did everybody get something different at this table?
First I got 27, then 81.
A 27 here and an 81. Did anybody get anything different?
I think it was a lot different because first time I didn't understand your instruction, but the second time I got it right. The cycle.
What number did you get?
I got 27.
27. That's surprising, isn't it? Some numbers seem to be repeating themselves.
63 the first time and 36 the second time.
63 and 36. Here there's somebody with a very big smile on her face. And that is what we want in the classroom, don't we? We don't want Uzmas who are anxious and worried. Is Charlie going to turn up with a microphone and ask me to? We want people who are confident.
The answer of the total of the answer with everyone is 9.
What about 9?
So everyone having 9 as an answer has got that particular.
I see. So there's something about all these numbers being in the 9 times table, I think I'm being told. So 9, 18, 27, 36, 45, 54, 63. And if we try again, and we look at all the numbers in the 9 times table, this time, there's a star at 9, at 18, at 27, at 36, at 45, at 54. All the 9 times table numbers have the same icon. And every time I refresh it, that icon changes. So now I've got is that a hand or a bird? I don't know. That all the numbers in the 9 times table again have the same icon. Goodness, that looks either like a ghost or something. Yeah, anyway. The journey is not over because I don't want children to leave my classroom thinking, how on earth did that happen? We've still got a bit of work to do. But you discovered that all the numbers were in the 9 times table without me having to tell you. So allowing some time for the students to explore, to share ideas, to talk to each other, has led us halfway to discovering how this works. And that, again, is at the heart of working mathematically. I better hurry up. Here we are. Multiple strategies. Joe Bowler, who works with Carol Dweck at Stanford University, often talks about how important it is to give students the message that there isn't just one way of doing maths. Often there are numerical ways, there are diagrammatic or geometric ways of doing things, and there are algebraic ways. And if you just think about it as that you can do things in only one way, you're sort of short-changing students. So I'm going to just give you one example. There's a problem that we have on the website, on Enrich, called 3 neighbors. 3 neighbors involves thinking about 3 consecutive numbers. So 5, 6, and 7, and if you add them up, they're up to 18. 14, 15, and 16 are 3 consecutive numbers, they're up to 45. 2, 3, and 4 add up to 9. 9, 10, and 11 add up to 30. And what you notice is every time you add 3 consecutive numbers, they always end up in a number in the 3 times table. 18 is in the 3 times table, 45 is in the 3 times table. If I add 1, 2, and 3, they're up to 6, which is in the 3 times table. If I add 99, 100, and 101, they're up to 300, which is in the 3 times table. So, I want students to notice that. I want students to be asking themselves, why does that happen? And I want to be able to offer them 3 alternative ways. So I work with 2 colleagues, one's called Liz and one's called Claire. So we're going to share our 3 different strategies. So Liz, is this working? So Liz thinks about it like this. I've got 3 numbers and they go up by 1 each time because they're consecutive. If I take 1 away from the biggest number and give it to the smallest number, then I've changed this and I've got 3 identical numbers. And when I add 3 identical numbers, I'm going to get a number in the 3 times table. So if I have 4, 5, and 6, I can turn that into 5, 5, and 5, which gives me 15, which is in the 3 times table. I'm always going to get 3 times the middle number. So that's how I knew that 99 plus 100 plus 101 was 300. It's 3 times the middle number. It's 3 times 100. 14, 15, 16 is going to be 3 15s, which is 45. So a diagrammatic way of explaining why you're going to get a multiple of 3 is really, really powerful. And we tend to value algebra, but actually, this often gives you much more insight. You understand and appreciate why it's a multiple of 3. Now, Charlie's method is also pretty good, just in case. So Charlie starts with the first 3 consecutive numbers, 1, 2, and 3, and then up to 6. And then he wants to get the next set of 3 consecutive numbers. So he adds 1 to that one, and 1 to that one, and 1 to that one, and gets 2, 3, and 4. So he's added 3 altogether, so the total goes up by 3. Now, if he adds 1 to each of those, he'll get the next set of 3 consecutive numbers. And the total will go up by 3 again. And then if he keeps doing that, always adding 1 to each, the total is going to go up by 3, and so he will just keep hitting the numbers in the 3 times table. 12, 15, 18, and he'll keep going, keep going, keep going. He'll hit 99, but he won't hit 100. He'll hit 99 when he's got 32 plus 33 plus 34. Looks like a picture Liz's method of having 33 in the middle. Now this also feels very convincing. Eventually you also want students to be fluent with algebra and confident with algebra so that they can write that 3 consecutive numbers can be represented as n plus 1, n plus 2. When you add them all up, you get 3 lots of n, which is a multiple of 3, plus 3. Or you might write that can be factorized. It's 3 times n plus 1. I want students to be able to be familiar with the 3 methods and confident with the 3 methods. I want to be able to say, okay, how would you use these 3 methods to work out what happens when you have 4 consecutive numbers? When you have 4 consecutive numbers, you don't get multiples of 4. But you can use this diagram to explain why you don't get multiples of 4 and to explain why you always get even numbers that are not multiples of 4. So you'll get 2, but you won't get 4. You'll get 6, but you won't get 8. You'll get 10, but you won't get 12. You get 14, but you won't get 16. So you can imagine using Liz's method, and you're going to get 2 left over always. And you're going to get, why do you always get even numbers? Because when you have 4 consecutive numbers, you have 2 evens and 2 odds. And when you add odds, a pair of odds, you're going to get an even. So there are lots of mathematical conversations to be had. And one of the things that Uzma is wondering, what stage do you start having mathematical conversations with the children? From a very young age. From a very young age, you can start talking about what happens when we add even numbers to even numbers, or odd numbers to odd numbers, or odd numbers to even numbers. Okay. I don't have time to talk about these 2 other problems, but your maths teachers can visit What's It Worth Mixing Lemonade and see examples of 2 other problems that can be solved in a variety of ways. So I don't want children feeling anxious in the classroom because they think there's only one way of doing it and they don't remember what it is. I want them to be playful and appreciate the value of doing things in a variety of ways. So the final thing I want to talk about is giving students the opportunity of working like mathematicians. And so I've described this as going on a mathematical journey. So exploring, which we did at the beginning, noticing patterns. You all noticed that there were numbers in the 9 times table, or you noticed that 3 consecutive numbers add up to a multiple of 3. Conjecturing is a fancy maths word for asking themselves questions, wondering whether something happens. Eventually, we want to generalize multiples of 9, but then we want to start justifying, explaining, convincing, and proving. And we're getting to there. And so I want to revisit the three problems that we've looked at before to give you a taste of what that might be like if our students have been working mathematically. When we think about the rote model, I want to go back to this idea that it's not just about conceptual understanding and procedural fluency. Doing this involves higher order thinking skills. HOTS, higher order thinking skills. When our students have made a start on a problem and they're making progress and they finish a set of exercises, we don't give them more of the same. We don't give them more of the same. We give them tasks which help them develop higher order thinking skills. This here is harder than that there. But this makes no sense if they haven't done that. So I'm hoping now we'll be able to go to got it, find the strategy to win, and it will make sense because you understand the problem, because you've struggled on the problem, because you've got stuck and frustrated, but you've been given some time. So let's have a look. We'll get some smiles on your faces again. So here we go. Reset. So of course with students we would have had a lot of time. And after discussing, initially we would have discovered that actually if you can get to 18 you're going to win. So actually the problem doesn't move from winning if you get to 23, it now turns you win if you get to 18. So how do you get to 18? Well, you want to get to 13, because if you get to 13, you're going to be 5 away from 18, and the computer won't be able to get to 18. But you're going to be able to piggyback on the computer's number, and you will be able to get to 18. So that's great. So that'll take the students a few more minutes to realize that, and then the realization that, oh, if we've got to get to 13, we need to get to 8, because from 8 the computer can't get to 13. And if we want to get to 8, we better start at 3, because from 3 the computer can't get to 8. So here we go. We've got a strategy. I'm going to start at 3 because the computer cannot get to 8. The computer's chosen 1, got to 4. I'm going to piggyback on that number. If the computer chooses 1, I choose 4, and I get to 8. The computer's chosen 1 again, so I'm going to choose 4 again. and I'm going to get to 13, and the computer's not going to be able to get to 18. Ha! Computer's chosen 1 again. Computer thinks I'm going to get bored. I'm going to choose 4 again. And I've got to 18, and the computer cannot get to 23. I mean, this is much more exciting than scoring a goal in football, isn't it? I mean, come on. We need to give students that experience of you win. Why don't students have that experience more often in maths classroom? It's the same as, performing in a school play, getting the applause from the parents, performing in a school concert and a choir, and being commended and congratulated by parents, scoring a goal, making a discovery in a science lesson. Here, I want students to have that experience. The last thread of the rope that I talked about was that productive disposition. If we want students to feel positive about themselves as learners, they need to have this experience every now and again. So, you may be curious, how on earth are we going to get the treasure in 3 goes? Here's how. I'm telling you because we don't have time. Uzma hasn't given us a whole day for working. If she had, you would have had time to work on this yourselves, okay? I'm just telling you where I'm hoping students are going to reach if we've given them time. Some students might start thinking, right, starting in the middle was a bad idea. I'm going to start at one of the corners. And it doesn't matter whether you start at 0, 0 or at 12, 0 or at 12, 12. It doesn't matter. I'm going to test these coordinates. I'm told I'm 9 away. Leave both on. Leave both on. Okay, 9 away. I'm going to do this as quickly as I can. I can be at any of these points because I can go, the grid lines are so unclear, I have trouble finding. Okay, so I can go 9 up, or I can go 1 across and 8 up, or 2 and 7, or 3 and 6, or all the way up to 8 across and 1 up, and 9 across and no. I mean, if this grid carried on to the left and below, the rest of that square of dots would be to the left and below. But because we're only working in this quarter, I only see one side of the square. And now, instead of choosing a point in the middle and finding that I could either go left or right, I can choose a point at one of the ends of that line. Oh, 18 away. It must be 9, 0. There's only one point that is 18 away from here and 9 away, and it's this one over here. And it took you 3 guesses, and even then the computer is wondering, oh, maybe it took you 3 guesses and you were guessing. You were just lucky. But I am convinced that I can always use this strategy and always get it in fewer than 4 guesses. And again, it's like scoring a goal, or hitting a 6, or making a good catch in cricket. I should use cricket analogy a lot more. Okay. Number jumbler. Where are we? Here we are. So there are various ways of explaining why you always get a multiple of 9. It made Amanda laugh yesterday when I showed her this. I'm going to do the same explanation. Is this working again? Okay. So one way of thinking about this, why do we always get multiples of 9? Well, imagine you start with the number 20. You have to take 2, you get 18. If you start with 21, you end up taking 3 away and you get 18. If you start with 22, you take 4 away and you get 18. If you start with 25, you take 7 away and you get... So, if I start with 29, I take 11 away. So whenever I start with the 20s, I can end up with 18. If I start with the 30s, I'm always going to end up with 27. Because 30 take away 3 is 27. If I go up by 1 to 31, I've got to take an extra 1. So as the numbers go increasing, I end up taking 1 more. So if I start with 40, I take away 4, I get 36. 41, take away 5, get 36. 42, take away 6, get... So, what made Amanda smile is I call this proof by exhaustion. because I'm trying all the possibilities. There are other ways to do with place value, but because we're not interested in the maths bits today, I'm not going to spend time doing that. But you can imagine, at least, I want students to feel that there is an explanation. I don't want them to think of maths as magic. I want them to think that there are reasons why things happen and that we can explain them. And so this proof by exhaustion, at least, is quite accessible. And you can see why this is always going to happen. I've got one more example before I talk about what your teachers can do when they get back to school. There's a problem that we have called tilted squares. I'm showing you this because there is a video on the website of a colleague and me working on this very problem with a group of students. They were 13 or 14 years old. And we worked on this problem for about an hour. This was a group of students we'd never met before. And if you want an example of how teachers can work in this way with your students, they might want to watch the video that we've put on the site. So it's in 3 parts. I'll show you how to find it. Actually, there's a link on the Pakistan page. So the problem was this. Students know, if we think of that square there as being a square with an area of 1, they'll have no trouble telling me that that's got an area of 4, and 3 by 3 has got an area of 9, 4 by 4, 16, 5 by 5, 25. And if I say to them 10 by 10, they don't even have to see it to be able to tell me that that will have an area of 100. 20 by 20 will have an area of 400. They've got a formula in their head, and they can sort of explain why. If you've got 20 by 20, you can have 20 little squares along the bottom, and you can have 20 rows. And they may not know what 20 times 20 is, but they can say, well, when I get halfway up there, I'll have 10 20s, and I know that that's 200, so another 200 make it 400. So they can picture it, they've got a formula, the formula makes sense, which is really important. But what about if we have a tilted square? If, for example, we go 2 across and 1 up, I happen to know the area of that is 5. And, sorry, it's not that I know, I can work it out. Because I've got a formula that I'm using. Oh, goodness. What happened there? Okay, sorry, let's go back to. Okay, so this one is 3 across and 1 up. And some of your students might think, well, I don't know how to work out the area of that. So, if you remember, we offer students some scaffolding. I want to help them get started. One way of working out the area of a tilted square is you box it in with a square. You work out the area of the whole square. In this case, the big square has got an area of 16, but you don't want the areas of the triangles, so you take them away. I've got 4 lots of 1.5, that add up to 6, and if I take 6 away from 16, I get the area of 10. And that's not the only way of doing it. Another alternative is you cut up your square into bits. And I would be doing this with students who know how to work out the area of a right-angled triangle, because it's half of a rectangle, and the area of a square, and they can work out that it's got the area of 16. So we've got a method for solving, for working out the areas of tilted squares, and we can go back and we can think about what happens when it's sort of 4 across and 1 up, 5 across and 1 up, 6 across and 1 up. And what about if it's sort of 2 across and 2 up, 3 across and 2 up, 4 across and 2 up, 5 across and 2 up? Can they find a quick way of working out the areas of these tilted squares without having to do all the boxing in and splitting up? Now the answer is yes, there is a way of doing this, but again, I'm not going to show it to them because I want them to play around initially by working on the ones that are just 1 up, and they will notice this one's got an area of 2, which is 1 more than 1. This has got an area of 5, which is 1 more than 4. This has got an area of 10, which is 1 more than 9. 9 is 3 times 3. this has got an area of 17, which is 1 more than 16. 16 is 4 times 4. They will realize that you always get 1 more than a square number. And they'll start making predictions about what's going to happen when we go 2 up. So if your teachers watch the video, they'll see that this is the journey that the students went through. And it finished with them discovering Pythagoras' theorem. This leads to Pythagoras' theorem. And it only took an hour. I could have started the lesson saying, a squared plus b squared equals c squared, which I imagine many of you remember from your old school days. And there is no pleasure in just spending time working out the missing side of a right angle triangle when you know that a squared plus b squared equals c squared. The pleasure comes from working on this and discovering Pythagoras' theorem. And before you complain that we don't have time to do all this, and the curriculum is full, and we don't have... Think about this. You can do this with 11 and 12-year-olds who just need to know how to work out the area of a square and the area of a triangle. And most 11 and 12-year-olds know how to do that. That's sort of where they start. So instead of giving them boring repetitive exercises where they work out the areas of several rectangles or squares or triangles, you can give them this, so they do the practice and they discover Pythagoras' theorem at the same time. They do it all at the same time. Wouldn't that be wonderful? So that is what I'm talking about when I'm talking about going on a mathematical journey, and it needn't take up more of the time. If anything, they've done Pythagoras' theorem a year or 2 earlier than they normally do. Sorry, I'm looking at what I've missed out. I've missed out a problem, but that doesn't matter. Okay, so when you go back to schools, what might you want to share with your teachers? If they want to know more about the thinking behind what I've been talking about, they might want to take a look at the what we think and why we think it page. So this is organized in almost the same, not in the same order that I've been talking today, but it talks about tapping into children's curiosity, what it means to think mathematically, believing that students learn if they get opportunities to discuss and collaborate, the importance of a growth mindset, and what our students are entitled to succeed and to struggle. And if they want to know a little bit more about this, I've put several links to lots of references of people who've done a lot more thinking about this than me. So curiosity and thinking, Dan Mayer, John Mason, Carl Dweck. Carl Dweck gave a TED talk, and some general reading. If you want to know more about Tired, there is an opportunity there. We also have a link to problems. I'm assuming you're all secondary teachers but we obviously have resources for primary teachers. But if you go to the secondary page, we've got curriculum-linked problems. So whatever subject they're about to teach, they can find resources. So they're going to teach them geometry. Oops, I must have clicked on the wrong thing there. I've got no idea what's happening here. Go back here. Curriculum-linked problems. If I go to geometry, here we go. They can find problems about angles, about construction, about perimeter. There we are. And there are lots of problems. And what we've done, which teachers might find really useful, which I didn't show to Karachi or Lahore teachers, so you've got a great one, is that we've mapped everything onto a curriculum mapping document. So we've listed the problems which are our favorite rich tasks. We call them rich tasks because it challenges the students to develop all 5 threads of the rope model. Okay? And so they can be looking at what it is that they're going to be teaching, and whether it's number, or algebra, or geometry, we've done the same. We've identified the problems that are linked to the curriculum, and they may find that really useful. All the links to this are on the Pakistan page, okay? So the one page you need to remember is enrich.maths.org/Pakistan 2024. So there's a bit of advice there about enriching the curriculum. And the last thing then is that if your teachers are convinced that this is what they want to do, they might want to sign up to our problem-solving school initiative. So again, there's a link to this on the Enrich page. And what we've done is, it's a very recent initiative, and all schools are welcome to join. There are no fees attached to this. And what we've done is, we've produced a charter to help schools reflect on what they are doing and what they need to consider doing in order to encourage more problem solving in their schools. So sign up to the values and ethos that they believe that all students can become better problem solvers. This will then inform the leadership and the professional development that is required, and that will then inform the curriculum, the pedagogy and the assessment, and influence the classroom culture they're going to want to see in their classroom, and how they promote problem solving outside of the school. So this is not a test. This charter is there so teachers can use it as a checklist of what they're doing. And if they'd like to sign up for the Problem Solving Schools initiative, then all we ask them to do is to go through that checklist, see where they are. Are they at the start of that journey, in the middle of their journey, or are they quite well along the journey? And to identify just 3 action points. And it's completely up to each maths department in each school or each primary school maths teacher to decide what the 3 action points are. And then every 6 months we'll invite schools to evaluate, to work out, to revisit their action points and work out where they want to do, what they want to do in the next 6 months, what they want to focus on, what do they want to emphasize, what they want to prioritize. It's not, there's no test, there's no exam at the end of it. We're not going to be checking up on schools. This was only launched a month or so ago, and we've already had 500 schools sign up. And what we do then is we offer some resources of professional development. My colleague Liz and I have written some resources to support schools who want to support their students to work collaboratively. In a couple of weeks' time, we're going to be doing our next webinar. Every couple of months, we offer a free webinar to all our problem-solving schools. So this is something you may want to do, talk to your teachers about. So I want to finish by going back to the slides that I had. And I think a lot of the slides there cover ground that we've covered already. So I want to just finish off with these. I want to give you a couple of minutes to talk to the person who's sitting next to you. If today's talk is going to make it's going to influence anything that happens at your school, if it's going to have any sort of effect, it's important that you leave here having thought about what you're going to do when you return to school, and with whom, when, how, why are you going to share what you've discussed, what you've heard me talk about. And more importantly, it's that we found that unless you do this within the next 2 weeks, chances are there are going to be no changes in your school. So in the UK, when I do something like this, I give a post-it to every teacher, and I get them to write something and stick it in their diary or they post a message and stick it into their calendar to remind them. So my invitation to you now, for the next couple of minutes, with your neighbour, think about what you might want to do when you go back to school, and commit yourself to doing something in the next 2 weeks, so that it can, all the trouble that Usman and her team have gone into to prepare a day like today, then has an impact. That feels really important. So, 2 minutes for you to talk to each other, to scribble some plans, or to type something into your phone or your laptop. What are you going to do? Who are you going to do it with? When are you going to do it with? Why are you going to do it? I'm very conscious that I've overrun, and that you're going to be able to carry on having these conversations at break time after Amanda has spoken. I think I'm just going to finish with this quote from David Wheeler. I don't expect, and I don't want all children to find mathematics an engrossing study, or whether they want to devote themselves to either in school or in their lives. Only a few will find mathematics seductive enough to sustain a long-term engagement. But I would hope that all children can experience, at a few moments in their careers, the power and excitement of mathematics, so that at the end of their formal education, they at least know what it is like, and whether it is an activity that has a place in their future. Thank you very much.